How fast is light? Well, light travels at 299,792,458 meters per second through a vacuum. No, not that vacuum. This vacuum. So, how did we even manage to calculate the speed of light? In this video, we'll be covering 4 different people who tried 4 different experiments to try and calculate the speed of light. First, let's talk about Galileo Galilei and his attempts at measuring the speed of light. Galileo is often considered to be the first person to try and measure the speed of light, all the way back in 1638. Galileo Galilei's design was simple, but heavily flawed. The experiment would involve Galileo and his assistant standing on hills 1 kilometer apart, 2 lanterns, 2 cloths to cover the light with, and something to time the whole experiment with. This is how the experiment would go. Galileo will start the timer and uncover his lantern. Light will shine out in all directions. Once the assistant sees the light, he will immediately remove the shutter from his lantern and the light will shine back at Galileo. When Galileo sees the light, he stops the timer. Using this experiment, Galileo concluded that the speed of light was at least 10 times faster than that of sound. This number was way off. The number that Galileo got was 1/1,000,000th of today's accepted speed of light value. What caused Galileo to be so far off with his number? 3 words: human reaction time. Say it takes about half a second for Galileo's assistant to remove the cloth when he sees the light, and then another half second for Galileo to stop the clock when he sees the light. When it takes this many seconds for light to travel 2 kilometers, that 1 extra second from human error really makes a difference. Next, let's talk about Ole Rømer, the Danish astronomer, and his attempts at measuring the speed of light. While studying the eclipses of Jupiter's moon Io, Rømer observed, as Earth orbited around the Sun and away from Jupiter, Io's eclipse would happen later than expected. Because of this, he concluded that the speed of light must be finite, which is contrary to the common belief at the time that the speed of light was infinite. Using this information, and knowing how late Io was emerging from its eclipse, Rømer was able to make a prediction on the actual speed of light. Rømer's speed of light, which was based on inaccurate data for distance between planets, was 214 million meters per second, which isn't too far off today's defined value for the speed of light. If Ole Rømer had the correct data for the distance between the planets, his number would have been surprisingly close, off by less than a factor of 2%. Now we're going to talk about Hippolyte Fizeau and Albert Michelson, who both had similar ideas for how to calculate the speed of light. First, let's talk about Fizeau's experiment. His method included a mirror, 4 lenses, a toothed wheel, a light source, a partial mirror, and an observer. This is how it worked. The light source would be turned on. The light would then converge through the first lens and hit the partial mirror and reflect towards the toothed wheel. The toothed wheel would be spinning, and the light would only pass between the gaps of the teeth. The light that passed through will then hit another lens and then travel 8 kilometers till it hits a third lens, hit a mirror, and travel back. At first, the observer will not be able to see the light that's being reflected off the mirror, because the light that passed through the wheel will be hitting off the tooth beside where it passed through. Only once the wheel was spinning fast enough would the light come back through the second gap. We now know the frequency of the wheel needed for the light to pass through the first gap and come back through the second. We can do 1/f to get the period. Because there are 14 gaps on the wheel, we can figure out that it takes 1/14th of a rotation for the light to be able to pass through the first and come back through the second gap. Multiply 1/14 by the period and you get the time it took for light to travel to 16 kilometers. Since velocity is equal to distance over time, we plug in 16 kilometers and divide it by the time it took for the light to travel that distance and we get the speed of light. Simple, right? Fizeau's method gave us a speed of 315 million meters per second. This is just 5% off today's value. Albert Michelson's method is pretty similar, so let's just run through this one quickly. This is how it worked. The light source on top of a mountain would be turned on. The light would then hit a rotating mirror and travel 35.5 kilometers towards a fixed mirror on another mountain. The light would then reflect back, hit the rotating mirror, and only hit the observer's eye if the mirror rotated 1/8 of its circumference. Now, if we run through the calculations again, Albert A. Michelson got 299,940,000 meters per second as his speed of light. So, how did we end up with today's value for the speed of light? Well, we chose it. A meter is defined to be the length of the path traveled by light in a vacuum during a time interval of 1 by 299,792,458 seconds. So since the meter is defined by the speed of light, we know exactly how many meters per second light travels. So, in conclusion to this whole video, the speed of light is pretty fast.